So since we're running late, we'll just go ahead and get started. So this is the 12:40 session for track 1. It's a 20-minute presentation, and then we'll have a 10-minute Q&A afterwards. This is being recorded. The presentation is, but the Q&A will not be. For this session, we've got Eric Lester from the City of Spokane, and he is presenting the Sharp Avenue Pervious Pavement Project. Eric?
Well, thank you, Mark. Appreciate it. And thanks to all of you for coming today. I want to also thank WSU for putting on the MuniCon this year. This presentation is for the City of Spokane Sharp Avenue Permeable Pavement Project. My name is Eric Lester. I'm with the City of Spokane's Integrated Capital Management Group. And before we get going, I want to make sure that I give credit where credit is due. Some individuals that were quite instrumental in getting the project off the ground. They include Mr. Ken Sammons of Gonzaga University, Rick Romero, Marcia Davis, and Mark Papich with Integrated Capital, and also our friend Mr. Doug Howey with Ecology. So as most of you probably know, Spokane is located about 230 miles due east of Seattle and lies about 15 miles west of the Idaho border. A shot of Spokane Coeur d'Alene corridor. And for any Jimmy Kimmel fans out here, we have proof that Gonzaga does in fact exist, in fact 2 miles from downtown Spokane. Our project is about 7 blocks in length and is the Gonzaga's northern border. A little bit of information about Spokane. Population 217,000, an area of about 60 square miles, and an annual precip of about 17 inches. So as many of you probably know, permeable pavement has been around for quite a few years, in fact probably over 40 years, and has been seeing increasing popularity over those years. The pavement is made by eliminating or reducing the finer grains in the mix design. And what we have here is a pervious concrete or permeable concrete. The pervious is the technical term. The shot here of the hot asphalt permeable pavement, also known technically as porous pavement. But regardless of how the aggregate is bound together, it is designed to work like a sieve, taking stormwater as fast as it could be applied. Cross-sectional view of, in this case, porous asphalt. You can see the water traveling through the pavement there. The upper layer is the permeable layer. Below is a dense grade. Picture showing a parking lot with dense grade on the left and permeable on the right. You can see the difference with the standing water. And I'm sure we've all been in this situation where we're traveling down the highway and a truck is kicking up water, road spray. On the left is the bad situation. On the right is the truck, same truck, traveling on permeable pavement. One thing we should know that with the whisking of the water from the surface, we've reduced or eliminated the potential for hydroplaning. And also, permeable pavement is a great way to reduce road noise. In fact, we can reduce it by 5 to 10 decibels with the use of permeable pavement. The driving force for this project, and the reason why we're all here, of course, is the potential for stormwater mitigation. Using stormwater infiltration can effectively remove contaminants prior to reintroducing the water into bodies of water such as rivers, streams, or aquifers. Also, as part of the project, We're taking a look at maintenance, issues with sedimentation, durability due to normal wear and snow tires, and proper cleaning of the permeable pavement. So permeable pavement, as we discussed, has included porous asphalt and pervious cement concrete. The benefits are an effective way to provide LID stormwater mitigation, to reduce winter maintenance costs, and reduce noise and road spray. Some limitations may be higher construction costs, though that can be balanced out with the fact that we're going to be able to eliminate stormwater systems, inlets, and piping. The potential for clogging is always a concern, and any kind of road deterioration due to heavy loads or turning movements. Where we have stormwater that's able to pass through our pavement, through a reservoir, and into the native soils, the water is further cleaned by cation exchange capacity, or CEC. Where we have the finer soil particles, as in clays, we get excellent adherence of heavy metals to those clay particles. As we move to bigger soil particles, sandy if you will, that capacity is decreased. Of course, the better the adhesion of heavy metals in the clay soils, we have lower porosity, and vice versa. Where we have good drainage, the capacity to suck out those heavy metals is diminished. So our project is the Sharp Avenue project. Again, it's up by Gonzaga University. The road it shows a skin patch over it, but it's in was in bad condition. And it had a 120-year water main that needed to be replaced. So the old roadway was a 4-lane arterial with street parking. ADT is a rather mild 7,500, and it utilized an MS4 stormwater system with the water being piped directly to the Spokane River. The project was designed in 2017 with an engineer's estimate of about $3.4 million. The low bid came in at $3.26 million and was awarded to La Riviere Contracting. The work was performed in 2018 and having substantial completion in October of 2018. So in addition to the 12-inch water replacement, we installed pervious concrete, both sections that will be sampled and tested and sections that will simply drain into the native soils. The project will also include a bioswale in the median. Porous HMA, again, where it's going to be sampled, that has been spec'd out, and otherwise it'll be into the native soils. And we've also included a control station to produce a baseline data. The project will include a 5-year stormwater sampling and testing period, and we'll also monitor pavement durability during that period. Project Geotech. Soil is a gravel, sandy, silty soil, or loamy. The average CEC is 12.2. Ecology recognizes 5 as being the minimum threshold. Infiltration rate is estimated between 6 and 8 inches, and the groundwater is below 25 feet. So here we have a section. This is between Lidgerwood and Astor. On the westbound side, we have our pervious concrete and ballast for water retention. It's draining towards the median, so this is kind of a backup stormwater system if this should somehow fail. On the eastbound side, we have a pervious concrete and ballast, And in the travel lane, we have dense HMA. The idea here was that we would check the situation with run-on water from the dense graded onto our Pervious to see what kind of problems arise from this interface here. Cross-sectional view. 9 inches of Pervious, 15 of the ballast. So I want to let you know that this 24 inches was spec'd out so that not for reservoir capacity, but rather to get below the frost line. So we don't have any issues with water being unable to seep through the subgrade. And we've also utilized a geotech membrane, or fabric rather, in the areas that will have in situ infiltration. Where we have testing, this will be an impervious membrane. Cross-section of the median bioswale. Dense graded on both sides, draining towards the median. Curb cuts to bring the water in. We have 18 inches of imported bio material. Grass and trees are planted. Our porous hot mix asphalt section. Again, both sides are graded to drain into the median in case there's a failure on either side. This drains into our native soils. This drains into or drains to the impervious membrane to be collected and sampled. Cross-sectional view. 8 inches of porous asphalt. We have a 2-inch choker course and 14 of permeable ballast. Again, we have geotextile underneath it, or a impervious membrane where we're collecting our sampled water. As part of the project, we are also testing a polymer additive. In this case, it's the Etonus polymer. We have 2% added and 4% added to the mix. Etonus is used quite a bit in Chicago. It's the first time out here in the Northwest, and it's the first time that a 4% additive has been tried in the U.S. So we're quite keen on seeing how that affects the concrete's durability. We're working with the Washington Aggregate and Concrete Association. They sponsored this test, and we'll be doing periodic inspections and testing throughout the next 5 years. Etonus was made specifically for pervious concrete. It's used quite a bit in Europe, and as I mentioned, Chicago's been using it the last 3 years. It provides improved mechanical resistance and also improves detriments caused by freeze thaw and by road salts. Just roadways, yeah. And there was no sidewalk done on this project, strictly curb to curb. View of our manholes. These are installed at each of the test locations. We're going to utilize, we've already installed the Teledyne IceCo auto sampler. It'll be installed here towards the top for easy access by our field crews. It's a wireless connection, provides SCADA communication. It will require a rep from the wastewater department to come out and sample the material, the water. The Teledyne collects about 9 liters of sampled water. And again, this is installed at each of the 3 treatment sites, the pervious concrete, the porous asphalt, and the bioretention, and our test section, our control test section. Photo of the ISCO auto sampler. It's about 18 inches in diameter and about 28 in height. Photo showing the installed ballast with the impervious layer below it. Picture the concrete going in. Obviously, it's being poured with forms. The device here is a vibratory screed to give us our compaction and our finish. And that's immediately covered with the visqueen to prevent any kind of dehydration. Shot showing the removed visqueen. Picture showing the impervious membrane with the slotted pipe awaiting ballast. ASTM-C 1702, I believe. Test being performed. Pre-construction shot. They're at Sharp and Astor. Picture taken of the completed intersection. Reconstruction of the pavement at Astor, between Astor and Addison. Post-construction, where this was taken just before the striping was installed. So as part of the project, we're going to utilize a quality assurance project plan, or QAPP. This is our guidebook to making sure our post-construction testing and sampling is done correctly. This was developed for and approved by the Department of Ecology. And we had approval just about 3 weeks ago. So the QAPP was developed to make sure that our project testing and sampling, as I mentioned, is done consistently to provide accurate and reliable results. Sampling, lab testing methods. The lab testing will be done by our wastewater folks. It specifies a qualifying storm event. It's, I believe, 0.2 of an inch to be a minimum storm event, and includes which elements to be tested. pH, water hardness, phosphorus, half dozen 8 heavy metals to be included, and gives the format and frequency for the reporting to ecology. The system has been normalized. In other words, it's cleaned out and is running clean, if you will, as far as there's no silt. We're currently calibrating the samplers. We should be done, I think, by next week. And if all goes well, we should be performing the official testing in May of this year, rather. And that's it. Any